So what we're going to do is we're going to talk about the magnetic field created by the simplest possible object that can create a magnetic field, similar to how we did so in an electric field. Well, in an electric field, the simplest thing that created an electric field was just a single point charge. And remember, a point charge was a charge that was so small that its size and shape did not matter. Here, if you just had a stationary point charge, it wouldn't create a magnetic field, so we have to get it moving. And the way we're going to describe that is imagine a whole series of charges moving in one direction, and their velocity never changes. It always continues at the same speed in the same direction. Now, physically, that can be a little bit difficult to create. The easiest way to do that is to have current run through a long straight wire. Since it's straight, the direction it flows will never change, it won't veer off. And if the current runs at the same rate through the same type of wire, then it'll just move at the same speed. So the simplest thing in this case is a long straight wire. And we're going to introduce the rules to figure out how to find the direction of the magnetic field it creates and the magnitude. Now, we did a similar thing with electric again, where we said, okay, we showed out the rules for the direction of the electric field created by positive or negative charge. And in that case, it was very simple. Positive charge always made an electric field that went away. And negative charge always made an electric field that pointed towards it. There's a similar pattern here, but it's much more complicated, and you have to use this right-hand rule to figure out the direction. And then we'll separately give you a formula to give you the magnitude of the electric field at some distance from the object that creates it, in this case, a current carrying wire. So let's talk about how to do this right-hand rule. I'm going to show my picture here in a second. Here I am, so that I can show you how to do this with your hand. Now there's two versions of this right-hand rule, the one that I prefer and the one that is more common. So I'll first go over the one that I prefer because I think it tends to be a little bit clearer. I've shown you the answer. I've shown you the magnetic field created by a wire at 4 different points. Now I'm going to show you how you can get that answer. And that uses this right-hand rule. Now here's how it goes. I first look at the current. Remember that this circle with a dot in the center means an arrow coming towards your face, or out of the page, or out of the slide, either way I describe it, which I'll show with my thumb going in that direction. Now, be a little bit careful, but this webcam is going to take the perspective of looking at me from the perspective of the screen, but I'm going to move my hand in the direction that I actually see as out of the screen. So this direction is out of the screen. That direction is into the screen. This direction is to the left. This direction is up, to the right, and down. Now, it might be a little confusing to watch the video. I suggest you follow along and your hands should move in the correct direction. So I want to have my thumb point in the direction of the current. And I always kind of do that thumbs up thumb where it points directly out. Okay. Now, my thumb is going to point out of the page. And now I have to ask, where do I want to know the magnetic field? The direction of the magnetic field depends on its location. In some places it's to the left, some places it's down, some places it's up, some places it's right. So if I want to know a particular answer, I have to ask a particular question. Where's the magnetic field at this location? So I'm going to choose to ask the question about the magnetic field above it. Say, what's the magnetic field up here? If my thumb is the wire, I'm asking for the magnetic field up here at the top where I'm circling. And the answer will come out to be the left. Let's show how you get the left. So once I have my thumb in the right direction, and I know which way I want to find the magnetic field, I stick my fingers directly flat towards that spot, so that my finger bones line up with the bones in my palm. Then I bend my fingers 90 degrees, like that. Then my finger bones now point in the direction of the magnetic field, toward the left. Okay? Let's repeat now off with the magnetic field on the left. If I do the same thing, my thumb will point in the same direction. I want the magnetic field over here to the left. I have to turn my hand so that my finger bones and my palm bones point directly towards that point. Then my fingers 90 degrees, and my fingers point straight down. Now, one thing that will help do this correctly is to know that there are certain directions it will never be in. And it's really never in the obvious directions, the directions that it seem like it really should be in. So first, let's take the example of the magnetic field above. Now, the most obvious guess, you might think, is that the magnetic field would be either toward the wire or away from the wire. Because in the case of electric field, it was either towards the charge or away from the charge. And that seems the analogous thing here. But that's never the case. The magnetic field is never towards the wire nor away from the wire. Now, second most obvious case. If it wasn't towards or away, maybe that's in the same direction of the current or against the current because sometimes it's flipped. That's also not true. Even though that's another direction that would be natural to choose, then towards the wire or away from against the direction of the current. So some direction along the direction of the wire, that it is not at all in that direction. And it turns out that your only options that are not at all in either of those directions are going to be your options. So here's what I mean. Take it specifically above. Towards and away from the wire or up and down. It's not at all up and down. In the same direction or against the current would be into the page or out of the page. And it's not at all in that direction. And the only direction that's not at all up, down, or into or out of is to the left or to the right. So it's only those two options, to the left or the right, are the two directions the magnetic field can be from this long straight wire. Now if I take the example on the left, where I want to find the magnetic field to the left of the wire, away and toward would be left, right. Okay, I use the mouse here, left, right. Same direction, opposite direction of current would be into the page and out of the page again. It's none of those options. And the only thing that's left over that's not at all left, right, and not at all in and out would be up and down. And so you can use this rule just to figure out, is it up or is it down? Now, the reason I mention that is that the most common way of doing this is to use the right-hand rule to figure out the direction of the magnetic field lines. Now, as you kind of saw with the iron filings, the magnetic field lines went in circles around the wire. And so what the common way of remembering it is to use your right hand to figure out which way do the circles run. Do they run clockwise or counterclockwise? And the idea is you put your thumb in the direction of current and your fingers will curl in the direction that the magnetic field lines run in, which is a fine way of remembering it. Now here's the difficulty. The direction that the magnetic field lines run is not the same thing as the direction of the magnetic field vectors at any given point. So while this picture right here implies the picture over here, these four different directions, for example, it's often not as obvious that those should be converted in that way, meaning that a circle counterclockwise in this picture means to the left on the top, down on the left, right on the bottom, and up on the right. That usually this, which give you the electric field vectors, is much more obvious. And since it is less obvious, I mentioned the fact that it can't be in any of these directions as an aid, because often what people will do is they'll ask, well, what's the magnetic field, say, above? And then they'll use the curling one. And they'll say, okay, well, it goes around counterclockwise, and well, I can't just say counterclockwise, it has to be like left, right, up, down, somewhere you can point with your finger, some direction like that. Clockwise, counterclockwise is not a direction you can point in. And they'll say, okay, well, okay, I curled my fingers. My fingers are pointing down. That would mean the magnetic field's down, right? But remember, the magnetic field up here at the top is actually to the left. And so this helps to remember that it can't be down up there at the top, because that would be either toward or away from the current. So if you've eliminated out all the other options, toward, away, and with the current and against the current, and you now narrowed it down, it's either to the left or to the right, then this tends to help you. You tend to realize, okay, well, this means to the left. Even though sometimes you can curl around all the way to here and it's still to the left above it, it's less likely that you'll be off by some angle. You can do either way, trying to remember the magnetic field lines or directly finding the direction of the vectors. I recommend this way. People tend to get this one wrong less often, but either mnemonic will work.